The title of our project is Obstacle Detection Device for the Visually Impaired. The name of the members are Lars, Stoeckhert, Jessy, Liam, Caufaglione, Maritsa, Rehma, and our advisors are Damodaran, Radhakrishnan, and Ping-Chuan.
Before starting the design of the obstacle detection device, we needed to determine what the driving factors of our design would be. After completing some research, we found out that most of the technology that is available for people with visual impairment aren't directly related to obstacle detection except for glasses and surgery, and any technology that is was found to be extremely expensive. In order to solve this, our two main goals were to decrease the price and make this device specifically intended for obstacle detection. Since we were given a budget of $200, one of the main driving factors of this project was making it within it. We decided to use cheaper materials and 3D print the housing, as well as use materials that we already had as a means to decrease the overall cost. When thinking about the overall design of the obstacle detection device, we wanted to make sure that the device would be lightweight, discreet, and small. The device was designed to be an extension of the user instead of just something that the user uses. We also wanted to make sure that the device could operate in all environments, so in order to do that, the housing was made to be shockproof as well as waterproof. In addition to doing research on technology related to obstacle detection, a survey was created in order to understand the public's knowledge on methods and technology used by people with visual impairment. This data was then collected and used to ensure that the device was designed as effectively, efficiently, and inclusive as possible. Since there were restrictions on where and how the survey could be distributed, the data that was collected remained inside the new Paltz community. Some important questions that were asked were participants' age, if they or someone they know has visual impairment, and how often they use certain devices and methods, such as a seeing eye dog, a white walking cane, and phone applications. In addition to that, we also tried getting feedback on technology that participants thought could be useful in order to get a clear understanding of which direction the project could go. After completing the survey, we learned a lot about people's knowledge on current technology available for the visually impaired, and also about possible directions this project could be taken in the future, like adding the ability to read text from faraway distances, as well as describe images.
For the device's casing design, we went through 3 iterations. For the first design, we decided to keep it simple. We designed it in a form where it would be watertight. There are 2 pieces, the lid and the base, that overlap one another to add an extra protective layer and will be attached to a safety vest to wear. For the first iteration, there is only 1 camera hole. However, for the second iteration, we added 2 more holes to incorporate a distance sensor, as we realized that the distance sensor is better for detecting further objects, while the camera is good for closer objects. This was the casing we used for the engineering design review. At this event, we received many feedbacks on how to improve the device. For the third iteration, we decided to separate the camera and the main microcontroller, as we are going to use 2 cameras instead of 1. So we mainly focused on designing the centerpiece to encase the main microcontroller and have everything else spread around the body outside the case. We kept the general shape of the design. Things we changed was taking out the camera holes and adding handles on the side, as we are incorporating it into a harness rather than just attaching it onto a safety vest. Here is a final rendering of the case with some of the main basic components inside. To test the quality and durability of the device's casing, we performed 2 tests. One of them is the humidity test, where we tested the water resistancy of the case. Using the ingress protection rating, we observed the condition of the case at each level. This case design safely passed the first 2 levels without any water seeping through. At level 3, water started seeping through the edges between the lid and the base, but nothing inside got wet. At level 4, the inside started to get moist, but not necessarily wet. Therefore, this case design is level 4 water resistant, which means it can be out in the rain for a short period of time. The second test we performed was a drop test, where we tested the impact resistancy of the case by dropping it at 5.4 feet repeatedly. At the 15th drop, the lid split in half. As you can see on the left, one of the edges is cracked, but still somewhat holding the pieces together. This also allowed us to estimate the lifespan of this design, which is about 5 days. To improve the durability and water resistance of the device's casing, other materials that can be 3D printed, such as PCABS or DURS, can be used.
The device itself went through 2 iterations. Our original design used an Arduino microcontroller to process simple visual input. It was cheap, but had cumbersome wiring, shoddy object detection, and was slow, running at less than 1 frame per second. In Senior Design 2, we invested in a Raspberry Pi embedded computer and a machine learning coprocessor called the Movidius Neural Compute Stick 2. This allowed for simple assembly, advanced object recognition, and a working frame rate of 6 to 8 frames per second. The software runs on OpenVINO, a set of Python libraries that allow the Movidius NCS2 to augment the processing power of the Raspberry Pi. The device is turned on by pressing the power button once, and turned off by pressing it twice. This demonstration shows a user wearing the device and attempting to track my movement. He is wearing a blindfold and headphones and has no way of knowing where I am other than from the vibrating motors on his chest. He easily follows my motion as I walk around him in a random path. The final iteration had to be haphazardly assembled due to our inability to 3D print the packaging, but it would have been roughly the same size and weight as our original design, except with the aforementioned increase in performance.
We would like to thank our advisors, Dr. Damodaran Radhakrishnan and Ping-Chuan, for all the help and supports they gave us throughout this project.